quick introduction here for Don Emerson, is the Chief of the Communications and Intelligence Systems Division at the National Aeronautics and Space Administration John Glenn Research Center in Cleveland, Ohio. She is responsible for leading and managing all research and development in the competency fields of advanced communications and intelligence systems for application in current and future aeronautics and spaceflight systems. Dawn has 37 years of experience as a research and development engineer and manager of multiple organizations. She earned her Bachelor of Science degree in electrical engineering from The Ohio State University and a Master of Science degree in electrical engineering from the University of Toledo. Go Rockets. Dawn, I'll turn it over to you.
All right, excellent. Thank you so much. Good morning, everyone, and I'm really glad to be here with you today. Today, I'm going to talk about our new aerospace communication facility at NASA Glenn Research Center. And, I think this presentation will align well with both Bill and Ned's speech. Theme that you're going to see through this presentation is really embracing and enabling digital transformation to improve efficiency and performance. Okay, are you guys able to hear and see me okay?
Yes, you're perfect. Thank you.
Okay, wonderful. Thank you. All right, next chart, please. Okay, the new aerospace communication facility is located in the west area of Glenn Research Center, if any of you are familiar with the center. It's a 54,000 square foot facility that was specifically designed to perform research and development of aerospace communication technologies and systems. I just took a picture of the facility last week, so you can see that the building is nearing completion, and we're scheduled to move in next spring. Next chart, please. All right, so kind of getting into the meat of things here. Here you see an artist's rendering of the new facility, and honestly, the likeness between the rendering and the actual building is quite amazing. The building consists of 25 state-of-the-art laboratories. I'll say all laboratories, there's no office space in here. And as I mentioned, the labs are tailored, designed to support the needs of our communications competency here at NASA Glenn. So just to talk about that for a minute here, at Glenn, we have expertise in all discipline areas necessary to develop communication systems for both space and aeronautics. The labs provide the infrastructure that we need to support these discipline areas. So just briefly, I'll touch on some of these laboratory suites, and then I'll talk in just a little bit more detail. But you can see here we've got system analysis labs. This is where we'll perform early concept definition of communication systems, network architectures, along with doing modeling and simulation to analyze these architectures. We also have a suite of labs that are dedicated to the various technology areas that really comprise a communication system. So at GRC, we are the agency lead for advanced RF technologies, and we have labs dedicated to the design, development, test, and evaluation of RF components and systems. Also at Glenn, we're also identified as the agency lead for autonomous and cognitive communications. So we have a suite of labs that's dedicated to developing signal processing techniques, as well as artificial intelligence, machine learning algorithms to enable these cognitive communication systems. We also have labs here where we'll perform network research. A focus there is on high data rate, delay tolerant networking protocols. And in addition to our RF communication labs, we also have a lot of expertise in optical and quantum communications. So the new aerospace communication facility has a suite of labs to develop optical communication components, systems, and we're also developing a quantum metrology lab and system test bed in this facility. Also, you kind of see the three-story part of the building. We call this the Microwave Systems Lab. And here we're going to have state-of-the-art antenna chambers and unique system-level emulation capability to assess the performance of communication systems in a recreated, realistic environment. So if you go to the next chart, and I'll go through these pretty quickly for time's sake, but I'll just touch in a little bit more detail on some of these laboratory suites. So, in our modeling and simulation lab, we have extensive tools to model, simulate, and analyze RF, optical, and quantum communication systems and architectures. I will say this is a really important area for us moving forward. As we think about some of our aeronautics projects, right, with advanced air mobility, or NASA's really pushing towards exploration on Mars. For both of those use cases, we need new communication infrastructure in order to support those missions. So this modeling simulation capability is very important for our upfront concept definition, architecture development and analysis of those new systems. So next chart, please. So this area, cognitive communications, and I think this is really relevant to the area that we're talking about here today. So this chart features our cognitive communications lab. At Glenn, we've done extensive work with reprogrammable software-defined radios, signal processing techniques to improve the performance and reliability of communication systems. Now we're leveraging all that work that we're done, taking another step forward, integrating in machine learning, artificial intelligence to enable autonomy and cognition to further enhance the performance of those systems. So if you, kind of an analogy that you can make is really looking towards kind of implementing interoperable roaming communication capability, for advanced air mobility or for lunar architectures. Another theme that you're going to see, through this is the development of ground test beds. This is a really important part of our facility where we'll be able to perform high fidelity hardware in the loop emulation of these cognitive communication systems, where we're able to test the system, how it reacts to realistic environmental conditions such as interference. So next chart, please. I'll just touch on this briefly. Another area that we work extensively in is in networking research. So our focus in this area is really on high rate delay tolerant networking protocols. And the next laboratory suite, kind of self-explanatory here, is the importance of system integration labs to integrate, test, analyze, and verify our space and aeronautical systems. Here's where we kind of pull things together, develop proof of concept systems. So next chart, please. So as I mentioned, in addition to RF technologies, we also have a suite of labs to develop and characterize optical communication components and systems. I will mention that these labs were designed with special requirements here, tailored to the type of research we're going to be doing in here. In our optical labs, they were designed with stringent vibration requirements and also temperature controlled. And this lab also has a unique 30-meter optical test range internal to it. And another growing and important area for us is in quantum communications. So for the agency, Glenn has been asked to develop a quantum metrology lab, so we're in the process of doing that. We're also developing a suite of tools to be able to analyze quantum communication systems and a system test bed in order to test these quantum systems. So next chart, please. We also have a suite of RF technology labs. This is where we can design, simulate, prototype, integrate, and test advanced RF components and systems. This includes RF circuits, amplifiers, phased arrays, and other advanced custom antennas. Some special features of this lab includes the fact that we can characterize systems up to 110 gigahertz, and also test from cryogenic temperatures all the way up to 500 degrees C. So that kind of talks about some of the labs that we'll have to develop some of our individual technologies. What I want to talk about, maybe spend a little bit of focus on here, which I think is really relevant to the discussion today, is our matrix capability. Matrix is kind of our acronym, stands for Multiple Asset Test Bed for Research and Innovative Communication Systems, which is a bit of a mouthful here. But matrix is where we really integrate many of these technologies together into an overall system, ability to do system level emulations. So, whether we're developing communication systems for spacecraft, for aircraft, those systems really must be able to perform reliably when they're subjected to environmental effects, such as weather, the propagation effects, multipath interference. So matrix is designed to accurately recreate these conditions to assess system performance in relevant emulated environments. The system also has robotic arms that's able to emulate the relative movement between assets, between receivers and transmitters. So through our matrix capability, through this system level test bed where we integrate in modeling simulation tools, we integrate in our artificial intelligence, our cognitive communications, our advanced RF systems. We integrate all of these together into an integrated communication system or into a larger system of systems, and expose those systems to the realistic environments that they would see. So think about here digital transformation. And, we really see this as an important capability for us moving forward. This capability would allow us to really perform, hundreds of virtual test flights in a controlled and automated environment, really, kind of reducing our risk and development costs moving forward. So next slide, please. And I'm just going to touch, for time's sake, briefly on two other facilities that we're developing in the aerospace communication facility that might be of interest to each of you. Here is a cutaway of the microwave systems lab, and you see two volumes here. The large volume is where we're going to put a horizontal planar near field antenna range. And that smaller volume is where we're going to put a compact antenna range. So next chart, please. I'll just touch on these capabilities very quickly in case there's any interest out there. But the horizontal near field range, really a world-class capability for NASA and the nation. This is where we can design and characterize antennas up to 10-meter class. and the frequency range up to 110 gigahertz, which I think is very unique, for NASA. I'll just mention here, this capability supports a broad stakeholder base, from earth science missions to human exploration, advanced air mobility. And I think I'll leave it at that. Next chart, please. And then we're also developing a compact antenna range. And this facility is really optimized to characterize antennas and communication systems, smaller, of less than 1 meter class antennas. Again, this has a frequency range up to 110 gigahertz, which supports trends towards higher frequencies. Now, compact range allows you to test in the far field the characteristics of the antenna in the far field in an indoor facility. These type of measurements are traditionally taken in outdoor ranges. In Cleveland, Ohio, that's not a real feasible thing. But not only can we, test the radiated patterns of the antennas, but this facility will also allow us to perform, testing of integrated communication systems. Something that's really, I think, relevant here as we look towards this Internet of Things, as we look towards these interoperable communication systems, we're looking more and more of leveraging the technologies that are being developed for terrestrial applications, for mobile broadband, and the protocols, the communication protocols that are used to support that are what we call these 3GPP protocols, the 4G, the 5G protocols that you're probably used to. This Cater facility is the accepted method or practice in order to use those. So as we look at, developing systems, both for space, for lunar architectures, for advanced air mobility, and we look to try to leverage those communication protocols, those terrestrial roaming, those protocols that allow us to do roaming, kind of implementing Internet of Things in the air and in the sky. Being able to test to those protocols is going to be very important. So next slide, please. I'm not going to cover this, but this is going to be, in your package, a lot of words here, but I highlighted our matrix capability. And I think, moving towards these system level automated test beds, these digital twins, this push towards digital transformation, this matrix capability, I think is going to be a lot of benefit to us moving forward. This is kind of a brochure, the next 2 pages, and like I said, I won't go into the details of this, but it talks about the capabilities of this facility in a little bit more detail. So I think this can be a very powerful tool. So if any of you are interested in learning more about it, we'd love to talk with you about it and any potential collaborations that you think would be beneficial. So with that, we'll move forward to next chart, and then the next chart. My last chart here. So I covered a lot of different capabilities very quickly. Again, I just touched upon, kind of our discipline areas in the communications at NASA Glenn, and the laboratories and facilities that we have to support that. Again, big push here, towards autonomy, towards digital transformation, not only in our technologies, but in our laboratories, our infrastructure that supports the development of those technologies. So if any of you are interested in, talking about these areas in any further detail or potential collaborations, I've listed here points of contact. These are my branch chiefs. that head up each of these laboratories and discipline areas. So please feel free to reach out. We'd love to talk with you. So thank you.